Good evening, everybody. This is Nighttime Mathematics Radio. This is Wednesday, March 25th. Let's get started. As always, you can just tweet questions to @NightMathRadio on Twitter, and I'll try to answer them here live on the show. For the moment, we've got an interesting question that came in from a calculus student who tweeted a page of notes that looked which were very brief. I mean, they're extremely well written, but very brief, and basically said, I have no idea what this even means. What are you talking about? So let's take a look at it. The notes are a very, 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 very short form of what are called the method of shells and the method of disks. So let's go through them in that order. Sorry, actually, let's go through them in the other order. So what In Its Time was asking on Twitter, it looks like this. Let's go over to it. Now, there's a whole lot of problems that come up where you're trying to find the volume of a shape. For example, say the shape here. Where the way you create the shape is you take some function that looks like any other function you've ever done in calculus. Say here we have f of x is equal to x squared. Over some range, say 0 to 2, and then you imagine rotating it around the x-axis. So you could imagine spinning it so that it describes the end of it here at, say, at x equals 2, describes a perfect circle around the x-axis. And that gives you this weird object that looks sort of like a Hershey's Kiss, where it looks, you can imagine it sort of looks like a nice circle at the bottom and then flutes in to a point at the tip. And the question is, how do you find the volume of such a thing? And it turns out the trick you use is a lot like the trick you used to find the area under a curve in the first place. Remember when you went back to find areas under curves, the way we introduced integration in the first place, if you had some function, say f of x equals x squared, is you imagine taking a whole lot of little rectangles, going up to the function, and you computed Riemann sums off of these things. And we noted that if you imagine making the rectangles smaller and smaller and smaller and smaller, the area under the rectangles gets closer and closer and closer to the area under the curve itself. And in fact, the limit will be the area under the curve. And that's how we originally developed integration, which initially seemed like, well, that's great, but how do you do that? And then, thank goodness, we came up with the fundamental theorem of calculus, which said it's just the exact opposite of a derivative. So what do we do here? Rectangles aren't much use. This is a three-dimensional object. We can't add up a bunch of little rectangles. What we can do, you could imagine, is adding up a bunch of little disks. What you can imagine doing is, we took various points along the curve, then each one of them we made a little teeny disk. So imagine taking a little cylinder. We know the reason why do we take a cylinder? Well, because we know the volume of a cylinder. Remember, the volume of a cylinder is equal to pi r squared, where that's the radius of the cylinder, times the height of the cylinder. Right. And then the idea is, well, so the question is, well, how big would this? If you imagine making a little cylinder right at some place in here, at some value x, what is the volume of that cylinder? Well, the radius is just x, right? That's from the x-axis up to x. So the volume is pi x squared times however wide you make this thing, call it delta x. Where you imagine you have some little teeny where delta x just means a little teeny a little bit of width, because these things aren't very big. These are really, really thin disks you're imagining. And you can imagine you can make something that looks like a sort of chunky version of the object you're interested in by just taking disk after disk after disk after disk. So you actually make a little model. And then, just as we did with integrals in the first place, we could say, well, what if we made those disks thinner and thinner and thinner and thinner? Well, if we made those disks thinner and thinner and thinner and thinner, in the limit, you would actually have the volume of the object you're interested in. And the cool thing is that's just an integral again, because you'd imagine taking the volume of each disk and just plotting it as a function of volume as a function of x. And now the volume really is just going to be exactly like it is before, exactly like what the Riemann sum you saw before. So what can we do here? Now that we've got this, well, what that means is if we want to add up all these tiny, tiny contributions to volume, we can do it by using an integral, just as we did before. So what we're saying is in the limit, this goes to the integral of from wherever you're starting to wherever you're ending. In this case, it was 0 to 2. Pi x squared. But we got to be careful. I made a slight mistake here earlier. The radius of these disks isn't x, remember? It's to the function, which was x squared. So it's pi x squared squared. This is the trick. It's pi f of x. And in general, it's pi f of x squared dx, or delta x, rather. And on the limit, that delta x becomes a dx, becomes an infinitesimal. And now we have something we can integrate. This is the integral from 0 to 2 of pi x to the 4th dx. And that we know how to do. This is just a normal integral at this point. The pi is a constant, so it falls out. And this is a nice integral that you've probably done many, many times by this point in the course. This is just pi over 5 x to the 5th, evaluated from 0 to 2, which 2 to the 5th is 32, 0 to the 5th is 0, so this becomes 32 fifths pi is our volume. That's the method of disks. And you can do this with, as long as the function you get is integrable, you can do this with any surface that looks like this. What if, for example, we were interested in the function y is equal to the square root of cosine x? That's a funny looking object. You know what cosine x looks like? It looks like, say, oh, sorry, I need a range as well. Say between minus pi over 4 and pi over 4. Well, at minus pi over 4, cosine x is 1/2. Sorry, facing out. At minus pi over 4, cosine x is root 2 over 2, and we're taking the square root of that, so we're at the square root of root 2 over 2, which, ow, 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 but you don't care for the moment. Cosine would just look like this, right? We go up and back down again. We're just at the square root of that, which is going to drive it closer to the axis. Sorry, it's going to drive it further away, because when you square things, they get closer. You square it till it gets further away. So you have a little cap like that. And we can actually plot it if we want to see that. Hang on, I've got a grapher here. If we want to see what that looks like, we could say, where's my grapher? I could say y is equal to the square root of cosine of x. Let me kill my other graphs real fast. There we are. And there's the shape. And we're interested, let me zoom in a little bit on this thing. We're interested in it from minus root 2 over 2 to root 2 over 2. Sorry, minus pi over 4 to pi over 4, which is 1 point something. It's about there. So it's this funny little hump like we drew here. And then we want to rotate it around the x-axis. So we'll get two big circles at each. Let me go back to my notepad. Get two big circles at each end. And then here we have the square root of cosine x. So if we want to set up this integral, it's the integral from minus pi over 4 to pi over 4, the range we're interested in, times pi r squared again. It's always pi r squared, because remember, the volume of a disk is pi r squared times the width, which is, dx in this case. So it's pi, well, what's the radius? Well, the radius is the function. It's the square root of cosine x. So square root of cosine x squared, which is nice because it gets rid of the square root, it stops hurting our heads, times dx. Well, that's equal to the integral from minus pi over 4 to pi over 4 pi cosine x dx. And that's pleasant. The pi falls out. The integral of cosine is sine. Evaluate it from minus pi over 4 to pi over 4. Remember, pi over 4 is 45 degrees, so sine and cosine have the same value there. They're both root 2 over 2. So this is pi times root 2 over 2 minus negative root 2 over 2, which is plus root 2 over 2. So it's just root 2 pi. Oops. Wrote down off the bottom of my page. And every problem using method of disks looks like this. What you're doing is you're imagining making a bunch of little disks to make the object you're interested in. You're taking the volume of the disks, and what you'd like to do is add them up, but again, you want to get the volume of the shape itself, not the pretend one you made out of disks. You do that by turning the sum over disks into an integral over infinitesimal disks. And where in the infinitesimal disk, the delta x becomes a dx, and now you can just do a straightforward integral. That's method of disks. That's the thing on the left of your page. Now, on the right of your page, you had a second kind of problem, which is called method of shells. Where do you use this? Well, in the problems we were just looking at, the problems on this page, the objects we were making were made by spinning the function around so that the obvious axis of rotation made disks. But there's another way you could spin the object. Instead of spinning around this way, you could imagine spinning it around the y-axis. And then what do we do? So let's take a look at that. So let's take a look at that same function we had before, y equals x squared. But now, instead of spinning it around the x-axis, let's spin it around the y-axis. So we get a weird little bowl. Now you could still do this, you could do it either way, as it turns out. You could do this either by integrating little disks again, if you make the disks this way, integrate up the y-axis, which you could do. That's a little bit strange. But another approach you could do is again, I'm going from 0 to 2 along this axis. I'm going from 0 to 4 along this axis, because y equals x squared. The other thing you could imagine doing is saying, well, let's take our little shape here, then spin it around this way to make a shell. So so now we're making a little cylindrical shell, where instead of the shell being infinitely thin, but with as we were before, now what we're imagining is that we're taking a little hoop with a finite height, but a little teeny width. So what's the volume of this thing? Well, the volume of this thing, it turns out, is going to be basically just the area of the shape you've made here, which is, if you look at you can imagine cutting this little, this looks like a strip of paper that you've wound up and taped. If you were to untape it, the length would be 2 pi r, right? Because that's the circumference of the circle. The height would be this thing. And now you say, but okay, but it's not quite, but that's an area. How do we get a volume out of this? So you imagine if you thicken it a little bit, it'll be very close to this times a little dx again. Now this one's a little bit trickier in this case, because the reason is, if you look at where the shell sits, the shell starts where the function starts and then goes up to the edge of the range. So this is going to be a little messier than the last one. In fact, this is going to be enough messier. It might be more interesting to look at the other side of it. Let's start with an easier problem. Then I'll go back to this one in a second. Rather than taking the bowl, let's take the easier one, which is this shape. shape trapped between it and the x-axis. You get the same shells, right? Because as you spin it around, you get this big open bowl. The shell's height is x squared, like before. So it's 2 pi x squared, which is the height, times the radius, which is just x. So it's, and really I put that in the wrong order. I put that in the wrong order to make it obvious. So it's really, this is 2 pi x to be the radius of the disk, to be the circumference, I should say, of the disk, times the height, which is x squared, times delta x, and we want to integrate that from 0 to 2. And that'll give us the volume of this sort of depressed bowl. And what is it? Well, it's easy enough to do. It's 2 pi 0 to 2 x cubed dx. So that's 2 pi over 4 x to the fourth from 0 to 2. X to the 2 to the fourth is 16. So we have, we should probably simplify this a little bit. So it's pi over 2 times x to the fourth from 0 to 2. So again, that's 16 pi over 2 minus 0, so I'll leave that off, or 8 pi. That's method of shells. The idea of method of shells is instead of summing up little disks, you're summing up, you imagine instead making it out of little cylindrical sections, which are, you imagine being infinitely thin as you spin them around. So you have what amounts to, if you imagine it almost like a toilet paper roll, if you can still remember those before things got bad. What you have here is the height times the circumference of the top, which is 2 pi times this radius. And then you want a volume, so you imagine it's times, it's going to be reasonably well approximated by that times an infinitesimal thickness. So if we go back to this original problem now, this was a simpler one. If you look back to this original one, now we have to sit there and say, well, what are the shells here? Well, at each value of x, the height of the shell is, you have the integral from 0 to 2, because that's, again, the range we're looking at. It's 2 pi times x, which is the radius of the shell at that point, times the height, which is 4, the top of the bowl, minus x squared at that level. Right, because x squared is the bottom of the shell. The top of the shell is up here at 4 times dx. And again, that's a nice straightforward integral. We could do that out. Make a little room over here. When to integrate that out, we have to multiply it through. That's the integral from 0 to 2 of 8 pi x minus 2 pi x cubed dx. And now you can use the usual trick. You can split the integral across the difference. So that's 8 pi times the integral from 0 to 2 of x dx minus 2 pi times the integral of 0 to 2 of x cubed dx. And from here you can just bang it out. 4 pi x squared, 0 to 2, minus pi over 2 x to the fourth, 0 to 2. 2 squared is 4, so that's 16 pi minus 0. That's 16, so that's 8 pi minus 0. So this whole thing is just equal to 8 pi, which is cool. Also, there's a cool effect here. You know, the inside and outside shells are the same, which is cool. Those are the methods of shells and the methods of disks. Again, all you're doing in each case is trying to find a volume by adding up little infinitesimal pieces of volume, either by imagining that the object has been created out of a set of coins that have been stacked, or a set of very thin disks, and then adding them all up using an integral, because you imagine that as the disks become infinitely thin, or in the limit as the disks become thinner and thinner and thinner, the sum of that volume of stack of coins will be the volume of the object itself. Or you imagine that you've modeled the object out of a bunch of, as I say, toilet paper rolls or something like that, very, very thin hollow cylinders. That's the method of shells. And again, the reason they look different is it just depends what the volume of an infinitely thin disk or shell is. The entire difference here is that the volume of an infinitely thin disk, like this, is pi r squared times a little delta h, the little tiny height, whereas the volume of an infinitely thin cylindrical shell like this is going to be very close to 2 pi r times the height, which is not negligible in this case, times a little delta radius for how thin the thing is. And you might be wondering where I'm getting this. You might be saying, that looks a lot like cheating. Because, after all, I know what the volume of a cylinder is. It's pi r squared h. So I have an outer radius and an inner radius here. Why am I able to just do this? That looks a lot like cheating to me. And the answer is, it is, but the only reason we're allowed to do this is we know we're going to be taking the limit where the radius becomes infinitely thin. Let's see what happens if you do it properly, just for fun. If we did this properly, the outer volume would be, pi r squared, pi r plus delta r squared h, right? Where delta r is the thickness of the thing. So this is the volume of the shell that's delta r thicker than the one we care about, minus pi r squared h, the inner shell. You think, well, that looks like really the volume of a cylindrical shell, right? It's the volume of the outer shell minus the volume of the inner cylinder, so why didn't we use this? Why can we get away with some nonsense like this? And the reason is, let's multiply this out. That's pi r squared h plus 2 pi r delta r h plus, this is just using FOIL, right? I'm squaring this thing out. Plus pi delta r squared h minus pi r squared h. The pi r squared h just subtract off. So that's equal to 2 pi r h delta r, or just put the delta r at the back, plus pi delta r squared h. Now remember, I'm looking in the limit where delta r becomes very, very small. And if delta r is becoming very, very small, delta r quantity squared becomes small faster. And this is what lets us get away with this. In the limit where delta r is becoming very, very small, the ratio between this term and this term goes to 0. So we can safely neglect this term. And in fact, in the terms of doing the thing, we can imagine if we divide off the delta r's as we would to do a derivative, for example, this is the only term that would survive. So that's why we're allowed to do this. This is an approximation that's reasonably correct as long as delta r is small, and becomes more correct the smaller delta r becomes. And that's why we can get away with saying, well, it's just 2 pi r h times a little thickness. Again, if we weren't planning to take the limit, this wouldn't work. If we were actually making a model using cylindrical shells, we would actually have to care about that finite thickness of the shells. But in the limit, it's all fine. Okay, let's take a short break here to see if anybody asks any questions and to make sure that In Its Time understood this explanation. If In Its Time has any more questions, please tweet them in. For example, if there's a problem you can't do based on this, please tweet it in, and I'll take a look at it after the break. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, it looks like Twitter's gone silent for the night, so I think it's time to end this show. If anyone has any other questions, feel free to tweet them to @NightMathRadio on YouTube. On Twitter. I'll try to answer them right here on the air. This has been Nighttime Mathematics Radio. So in this strange world where school has sort of gone away, but all the homework keeps going, stay safe, everybody. Good night.